Introduction to Piping Vibration, Understanding the Basics of Oscillations and Mechanical Waves. What is vibration? Simple spring mass system, diagram and key formula, RMS and displacement, why vibration analysis matters. Vibration is defined as an oscillatory motion about an equilibrium position and is a common phenomenon in mechanical and structural systems. It occurs when a system experiences a disturbance and then oscillates due to its inherent properties of mass and stiffness. Vibration can be beneficial in certain applications, such as in musical instruments or vibration-based sensors, but in engineering systems, uncontrolled vibration often leads to detrimental effects. These include fatigue failures, noise issues, and reduced operational efficiency. Understanding vibration is critical because it allows engineers to predict and mitigate potential problems before they escalate into costly failures. The study of vibration involves analyzing parameters such as amplitude, frequency, and damping, which collectively determine the severity and nature of the oscillatory motion. By comprehending these fundamentals, engineers can design systems that minimize harmful vibrations and ensure structural integrity and safety. A simple spring mass system is often used to illustrate the concept of vibration. In this model, a mass is attached to a spring and displaced from its equilibrium position. When released, the spring exerts a restoring force that causes the mass to oscillate. The frequency of this oscillation is known as the natural frequency, which depends on the stiffness of the spring and the mass of the object. The formula for natural frequency is given by natural frequency or Fn equals 1 over 2 pi times the square root of spring stiffness or K over the mass or m, where K is the spring stiffness and m is the mass. This example demonstrates that very little energy is required to excite a system at its natural frequency, making resonance a critical consideration in design. If damping is present, it dissipates energy and reduces the amplitude of vibration over time. Understanding this basic system helps engineers predict how real-world structures will respond to dynamic forces and avoid resonance conditions that could lead to catastrophic failures. The diagram of a spring mass system visually represents oscillatory motion, showing parameters such as amplitude, RMS, root mean square, and peak-to-peak displacement. RMS is particularly important because it reflects the average energy level of vibration, which correlates with dynamic stress in components. The natural frequency formula, natural frequency or Fn equals 1 over 2 pi times the square root of spring stiffness or K over the mass or m, highlights the relationship between stiffness and mass. Increasing stiffness raises the frequency, while increasing mass lowers it. These principles are foundational in vibration analysis and are applied in designing machinery, piping systems, and structural components to ensure they operate safely within acceptable vibration limits. Engineers use these calculations to avoid resonance, which occurs when excitation frequency matches the system's natural frequency, leading to amplified vibrations and potential failure. Root mean square, RMS, is a statistical measure used to quantify the magnitude of varying vibration signals. It provides an average value that represents the energy content of the vibration, making it a reliable indicator of potential fatigue damage. Displacement, on the other hand, measures the physical movement of a component during vibration. Peak-to-peak displacement shows the full range of motion, which is critical for assessing clearance and avoiding mechanical interference. While displacement is more noticeable at low frequencies, velocity and acceleration become more significant at higher frequencies. Engineers often rely on RMS velocity measurements because they correlate directly with dynamic stress levels, which influence fatigue life. Understanding these parameters enables accurate assessment of vibration severity and informs decisions on corrective actions such as adding damping, changing stiffness, or modifying operational conditions. Vibration analysis is essential in engineering because it helps prevent structural failures, reduce maintenance costs, and ensure operational safety. Uncontrolled vibration can lead to fatigue cracking, fretting, and loosening of components, which compromise system integrity. By predicting vibration behavior, engineers can design systems that avoid resonance and excessive dynamic stresses. This proactive approach enhances reliability and extends equipment life. Vibration monitoring during operation also provides valuable diagnostic information, enabling early detection of issues such as misalignment, imbalance, or component wear. In industries like aerospace, automotive, and energy, vibration control is critical for compliance with safety standards and for optimizing performance. Ultimately, understanding and managing vibration is a cornerstone of sound engineering practice, ensuring that systems function efficiently and safely under dynamic conditions.